Bitonic sequence where the number of processors, and it is also called a sorting network for the reason that it is really targeted for running n things through a network of n things with several stages, right? N things in each stage, and n things were very simple compare and exchange. It takes two inputs, and the bigger one goes up and the smaller one goes below, or the reverse, depending on whether you're on the lower side or the upper side. What would you do if you didn't have that network, right? Meaning that I give you Bitonic sorting to implement, I give you n things to sort, and you have only p processes. What would you change? First of all, how long does the algorithm take? For n things with n elements, n processes? Log squared n, right? That's the time, and n log squared n is, sorry? And the work is n log squared n. What will happen if you have p processors but n elements? What would you do? What is it that would be different?
Since if the work is order n, you have
order n in what? In each stage. Total work is n log squared.
No, n log squared. So I mean, the way we discussed it already, with P, to convert algorithms to P processors, then each processor will stand as a proxy for.
Something similar will still apply, right? But sometimes when you look at the exact way in which you model, so there is a default algorithmic way which we've talked about earlier, and that can be done. Sometimes that takes longer than it would take with, this is not an example of that, by the way. It takes, if you carefully structure the computation, you'll see that it still turns out to be more efficient than the brute force mapping of k work to p processors at each step. Okay, so here in this case, I'll leave it at that. You can in fact do the same thing. You map the work of p things, rather n things among p processors. But just, I can't resist going one step deeper. What would each processor be doing? So let's take one step, and similarly you can do others also. We have one Bitonic sequence, or one half of the Bitonic sequence and another half of the Bitonic sequence, and this is longer than p or 2p, and you have to compare. You would have each processor compare some n over p of them. Which n over p? Or does it matter? In the original simulation that we discussed earlier, it doesn't matter, right? You simply do p things, p steps, or n by p things over n by p steps, and all steps are the same. But on real machines, that won't be the case.
So will it be n by 2p from one side and n by 2p?
That it would be, but which n by 2p? Right? You can take every alternate, you can take blocks.
It depends on the what underlying hardware, right? So for CUDA it will be different maybe.
So let's talk about CUDA.
we prefer so that each access will be from different banks by each processor. So,
since we are going there, would you want to do it in global memory or shared memory?
Shared memory.
What is the step for a given processor? Read one element from there, read one element from n by 2 apart, place, compare the two, and the bigger one goes here, the higher one goes there. Right? You're just swapping those two things. How would it work if you brought it in shared memory? You bring this in shared memory, bring that in shared memory, swap it in the shared memory, and then write it back. Do you save anything? Not really. Right? You just did an extra transfer through shared memory. In this case, it's an ideal case for just directly doing this in global memory. So in which case, banks are not visible, right? Shared memory banks are visible, but global memory banks are not.
Can you just put on a slide for the algorithm?
This should tell you, right? Or you want the picture slide? So that's picture slide. Second sequence is stored at a distant memory from the first sequence. The pairwise sequences are different at starkly different locations. So when you read two things, you will be reading from different locations, but many threads may be reading multiple things, and you would want those things to be read in blocks, right? Which suggests that all the different threads reading, suppose your block size is k, then k threads reading k different things. Alternately, meaning strided, first thread reads the first thing, second thread the second, the third thread the third, and so on, would make sense. If instead you said the first thread gets one block, right, element number 0 to element number 28, whatever, n over t is, then when you read element number 0, the next thread is reading element number 29. Right? So doing this in blocks might seem like a good idea, but isn't always. So if you look carefully at how to partition, then you can get better speedups. Okay, let's get back to more sorting. Bitonic it's not very efficient, right? At least work-wise, n log squared n is not that great. We already know of a better sorting technique. What is that? Optimal merge sort, right? Where we were able to merge two lists in log n time with n work. If you use that to merge sort, I think we'll come to that later on in the slide. We would get better than n log n, right? Log n stages, each stage taking log n time. What would be the total time spent? Log n, log n. And the work?
Better than that.
Okay.
It will be better than that? No, the time.
It's log n, log.
Time is log n. What is work?
Log n, log.
N log n.
N log n, log. N log n.
How long did it take you to merge work-wise. Merge two sequences of size order n each. N log n, right? That is the amount of work you will be doing at each level of the merge hierarchy. And there are how many levels? Log n levels. Right? So it's n log n log n. So it's not optimal, but it's better than this. This is n log n versus n log n log n. We'll get to also something that takes log n time and n log n work in parallel. Okay, it's a slightly complicated algorithm, but we'll talk about it. But looking at some of the simpler methods, which sometimes will run faster because they're easier to implement, and at least for relatively average number of elements, they work quite well. One of them is batchers odd even merge, which is question.
Yeah. So when the number of elements tends to go too large, can you not use some bucketing based sort, which is linear?
Bucketing, typically in practice, all reports say that bucketing is faster than any other sorting technique.
So even with, complexity wise, you typically have order n plus h if you have h buckets and n elements.
Complexity wise, it's a question of how long does it take you to compare two things. And the truth is that whenever you talk about things, you talk about integer keys or something of that sort, in which case comparing two things takes constant time. But in general, once you bring, and we never say, we say n log n comparisons, right? If you start to really grow big, then comparisons don't take order one time. Then it starts to be n log n times the comparison time. And then you have to compare that against, so once we are talking about really large numbers, compare that against radix or bucket sorting, right? How will Google, bubble sorting work in parallel? What do you do in bubble sorting? You keep checking pairs, and something that's at the top might reach the bottom. Then you start again and you start again, you do this n times, and then people are at the desired designated places. If you do that in a parallel setting, it doesn't quite work, right? It is kind of inherently sequential. You compare A and B, then you compare B and C, then you compare C and D, and so on. It turns out that there is a parallel version of it, and it doesn't have to be sequential like that. What you do is you take pairs and run them through this compare and exchange that we have just talked about. So you take the first element, or let's say 0th element and the first element, you compare them and swap them if necessary. Then you take in parallel second and third, fourth and fifth, sixth and seventh. So each pair, this is called either, depending on where you are starting the index, even phase or odd phase. And then the other phase, the next phase, would be the odd phase or the even phase, in which instead of taking 0, 1, you take 1, 2. Right? So you leave 0 alone. You figure out between 1 and 2 who is shorter, who is less, goes first. The more thing goes later. Then 3, 4, 5, 6, 7, 8, and so on. And so these odd and even phases make up one stage. You do this n times and your list will be sorted. Okay, I'm not going to formally prove it here, but you can intuitively probably see it. How long will this take? How many, what is the time per stage? Constant time. I said do it n times, so order n stages. So total time is order n, and work in each stage was order n, and so total work is n squared. Can it be better? It isn't that bad work-wise, right? You did n stages, each stage did order n work, and you end up with, it's not optimal in the sense of n log n, but considering that we are starting at bubble sort, that's what we would expect, right? N squared. But can you think of the time being better than this? Can it be better than order n?
Engaging all elements at all times.
Okay, I'll leave that as an exercise. You can improve it, and we'll talk about that next class. Which means I should not be talking about these slides. Again, you'll get the same question as before. If you had n processors, or rather p processors, n elements, what would you do? How would you put things together? And one thing that I forgot to mention when we were talking about the same thing in the context of bitonic sort, that things that typically, things that you would do locally, meaning two processors not sharing data. And whenever you do one compare exchange, you are really talking about two processors' data being compared and exchanged. When you have, so backing away from this just for a minute, if you had to sort n things, and I knew that locally I can sort things really fast, comparatively, in the context of not having to send data across to another processor and interacting with another processor and all those things. How would you structure your algorithm?
Something like quicksort.
If you did quicksort, then what would you have to do? I'm kind of running ahead of myself because there are some slides later about this. Since we are talking about it, I'll discuss it here. So in quicksort, what would you have to do?
Why quicksort? Because we don't have to merge afterwards. So we just divide work so that it will be in independent batches, and then just give the machines to do the sorting locally.
Right. And that's an excellent algorithm. Only after you have separated them. Problem is, separating them takes too much time, typically, again. There are variants where you don't insist on separating them into p equal parts. If you want to do it in p equal parts, then you are going to spend more than what you will make up for later. But if you are willing to say, maybe if I am between p and 2p or p and 5p, something like that, then you can separate them out reasonably well. And after that, it's great. Everything is local. Okay. That's one approach.
You're saying that there's division at the root node, at whoever has the data region.
No, we assume that the data, so again, we have to talk about in terms of whether it's a PRAM or communication model. You are thinking in terms of whether it's a communication model.
So it's sending data.
Well, sometimes I'm not very precise, but it means talking to other processors, sharing data, right? Even in PRAM model, there is a notion of local memory that everybody has and shared memory. where you have to write if you want it to be visible to others. So when I'm talking about sending data, I'm talking about writing it into shared memory or physically sending it using some communication network. So in both cases, doing it locally is much faster. Right? Think of MPI, you would rather do it on a given machine than figure out which part of data is being handled by the other person, which part is being handled by me, and then compare some things from my data to some things from their data. Doesn't matter whether for that I have to seek the other person's data. That in a communication network, that's the typical approach, right? Why I have some data, the other person has some data. I take the other person's data, I give my data, and then I somehow, for example, do the comparison, keep the lower ones. That guy does also the comparison, keeps the higher ones. Okay. There is repetition of work here, because both of them are making the same comparisons. Alternatively, you could make the comparison and send the lower ones or the higher ones to the other person. That has, why is one better than the other, or what's the comparison? Latency, right? You would rather in the beginning exchange the data and not wait for other person to compute the result and then give you the answer. You would rather in the meantime compute it. Again, that's not always a one-way street. It again depends on the context, but generally if you wouldn't be doing anything else, you might as well use that time to redo that piece of computation and save the communication. We have talked about this before also. Okay, so that's one. What are the other ways in which you can make things local? Merge can also work like that, right? I take P sequences, sort each of them locally on the P processors, and then I've got P sorted things and I want to merge them. Okay, so in this case, this analysis is based on the fact that I have taken this data locally, I have P sorted things, and then I want to do compare exchange among these sorted lists. Coming to this business of fast sorting, ultimately the business of sorting is to find your rank. Right? I want to know, given this list of unsorted things, I pick out item number 6 and say, how many things are less than me? And I know my position now. I just put myself over there. How fast can we find the ranks? For example, if you had n-squared processors. We've done things of this sort before. Go look up your notes. Sorry? Whatever it was. I don't want suppose I gave you n-cube processors. How fast can you sort? Not sort. Find the ranks of everything. So remember that when we were merging, we were actually finding ranks, isn't it?
They were sorted.
Sorry?
They were sorted.
But they were all finding the ranks when they were sorting.
But the individual subnets were sorted.
Sorry?
The two lists were sorted, and finding rank in a sorted thing is easier than finding in the unsorted.
Okay.
Then you know the position. Just need to take two positions.
That is correct. I was again maybe getting ahead of myself. When we were merging things, we were finding ranks in sorted things. But okay, so this we haven't done before. I was thinking that we have already discussed this before. If it is unsorted, I've got an unsorted list and I want to find the rank of a given element. So this probably needs a little bit of thought time.
Unique element.
Let's assume unique. That sometimes makes thinking about things easier, and then you can extend it to non-unique things also.
For each element, there are n processes, and each of the processes is the nth element, ith element.
So with
Less than
Hang on.
if it is smaller than the element being considered, it writes a 1 in the array, and then you do a log of reduction.
Find the first one.
You want to sum the number of.
Okay. So for every, so we are trying to find the element, a rank of one element right now. Okay. Maybe others can be done similarly. One element's rank, you compare it to everybody else, right? And you figure out how many elements are compared to 0. So when less is 0, positive means 1. It's actually typically the other way around, but doesn't matter. How do you count the number of zeros? Log n is one way, but that takes how much work? Does it need n squared? With n processors, you can do this in log n time. With n work, you can do this in log n time. Can you do better?
I keep a variable count, don't at 0, 1, and I just update it. If I see that this number is less than the, I update the count.
Update the count atomically. That doesn't really even belong in PRAM. There isn't an atomic write kind of thing, so everything is synchronous. Sorry?
only for zeros.
Fixed sum? Prefix sum. We probably need to stop. We'll continue this, but there was something that I needed. What did you just say? You. Atomic, right. If you think about it, an atomic update is a sequential operation, right? So if n people do atomic updates, you are doing order n operations. So that doesn't belong here. And sometimes we do that because we need some consistency and all that. But don't think atomic as your first choice of things to do. Okay, let's stop for just a minute and think about what prefix sum, or for that matter, how n squared processors help. I give you n squared processors. Can you do something with it?
Using 8 processors for one element, you find it in log n time trivial using reduction.
With n processors, log n time, yes.
And if you have n square processors, then still the log n time for the whole array.
Then you haven't used the n squared processors, right? Oh, you mean to find the rank of everything? No, I mean find the rank of. Okay, this question is asking how fast can you find the rank of A in A, the entire all the list elements. So yes, with order n squared things, it can be done in log n time, and that would be n squared log n time and log n, sorry, n squared log n work and log n time. Right? So time is good, but n squared log n is just not acceptable as work. But back to the question of if I had n squared processors, could you do better? For one element. One element, and I want to know the rank of that element among all the others.
When we get a sequence of zeros and ones, then we divide the sequence into token chunks of token size. Then we sequentially count the number of zeros, number of zeros of one and log of token time, and then again Thus, we have 210 numbers which we have to count using the tensor.
But
Taking log is
root n using root n things, right? Because then you're still using n total number of processors.
here using order of n, but we have reduced n here
How exactly?
because you have find the number of zeros in one chunk using the sequential algorithm. So you are using only one processor on one chunk. So you're using number of
Then you have taken root n time.
no log of root n time that.
Number of zeros using a sequential processor, right? If I give you an array with zeros and ones, and I give you one CPU, and I want you to find how many zeros there are. Can you do it in log n time? Can't be done, right? There are n things. You have to look at n things. Without looking at n things, you couldn't tell how many zeros there are. Okay, I'll come back to this.
So in concurrent write model, suppose we have to do OR. So OR takes order one.
Order one only.
The same thing can be applied
How?
just to find out the maximum.
You are on the right track, but
And then
how?
just find the maximum and then
Maximum.
yeah, maximum in the sense that maximum index of the somehow do or by all the n processes, the group of n processes, and then
Can n processors determine if my rank is 3?
Yes.
Similarly, some other n processor determining my rank is 4. Okay, I don't want to get stuck on this problem for too long. All right, so parallel quicksort, we have talked about this. The main issue is in how do you divide an element or a list into some p subsequences. In the traditional quicksort, we find a median, right? When we don't want to spend the time finding the median, what do? We guess the median, right? We randomly pick. Can you do something of that sort? If you randomly pick p things, what is the probability that the resulting partitions are relatively uniform? Actually, it's not very high. I'm not going to go through the math. For 2, it is yes. If you pick among n things one element, then the probability that you have even distribution where even is a fixed ratio is quite high. Okay. That cannot be said if you have to pick p things with all the p, right? It's going to get multiplied. The probability this as well as this, as well as that, as well as that lies within some range. So there are, you do need, if you are going to use that process where you say, I'm going to choose some number of elements and I'm going to make sure that they are relatively load balanced and then eventually let the processors process them, then you have to be careful about how to sample it. Okay. The alternative is you proceed in the standard binary fashion. Right? I divide it into 2 parts. and let the two parts be handled by half the processors. Okay. Now, if I divide it into two parts, two things have happened. One, I have, with good authority, that the two sides are relatively balanced, and whatever imbalance there is going to be hidden across many processors. In fact, you can even say that so suppose we say that we allow one half to be at most twice the other half. Then when you subdivide that into two subproblems, and you have figured out that it is the worst case where one half is only n by 3, the other half is 2n by 3, then you take p by 3 processors, assign it to one half, and two p by 3 processors, assign it to the other half. Okay. You can do some of that also in the case of when you're breaking it down into local. So you take some samples and you say, now this is, sorry, I should say you cannot do that if you're dividing it into p elements, p sublists, because you have said, okay, if my sample allows them to be within n over p, let's say n over p times 0.75 and n over p times 1.25, or 1 over 0.75, whatever that is, then you want to make sure that longer lists get multiple processors. But you have just said that each list is going to get one processor, which is now going to work totally locally. Okay, so there is a balance to be had. At some point, when you starting to get smaller and smaller and smaller number of processors, might make sense to go ahead and subdivide it into p processors, and then let each handle it in a kind of purely local basis. But when you have large number of processors, for example, at the beginning, you want to subdivide it into smaller chunks and then subdivide your set into working on the left half or the right half. Okay.
So we have like lots of processes to find out the medians as well. Can we not
Yes, you do.
find more medians more accurately?
You can, right? Again, as one of your friends will tell you, median finding is still hard, but you can do it faster than you would be able to do it on a sequential processor or a single processor. Okay, so back to the business of trying to separate things. I have somehow chosen a median, I guessed a median, and now I need to make sure that this list is going to get divided into two halves, and then I'll say processor 0 to n by 2, or whatever that number I have decided is, go work on the left half, and n by 2 to n work on the right half. What is that algorithm?
Already divided it. Okay. So doing that prefix something. Okay. Then we
That's the, I just want everybody to be at the same point. How do you divide it? We will take every element and ask the question, are you to the left or the right of the median? Right? You can do this in parallel. Some will be on the left, some will be on the right. Where should they be stored?
Find the index using prefix sum on the array which belong. Okay. So if you write a 1, if you belong to the left side, do a prefix sum on that, so you get the indexes.
Okay, so you simply write 1 or 0 in your respective slot, and I want to find how many zeros there are to the left of you, right? Meaning how many evaluated to the left side before you, and which means they should, this is kind of stable also. You're going to keep the things that were to the left of you and want to go in the left half to remain on the left of you in your half after the partitioning. And so you do the prefix sum, you count how many people evaluated to less than the median on your left by looking at your prefix number, and that is your position. Okay, now what was your question?
So suppose now we know that how many things are exactly smaller than the p-word. So then can't we divide the number of processors, in that ratio, the smaller divided?
Yes, yes.
So then what's the use of median to divide it into equal number of, or almost equal number of executions?
That's why I said that almost equal is not that critical when you're talking about parallel processors.
We can divide them in the exact ratios, smaller divided by total and bigger divided by total.
But whenever you talk in terms of real processor, real machines, be it CUDA machine, it's not as true of, it is also reasonably true of Intel machines. It was definitely true of the old parallel machines, which was M-cubes, mass powers, and connection machines, the kinds we've talked about earlier. Processors are typically some power of 2. Okay, and so if you keep the divisions in some power of 2, then integral division is somewhat easier. That doesn't necessarily mean that equal division is required, but if they had this equal, so suppose either it was half-half or 1/4, 3/4, then you probably get a much better balance than 1/3, 2/3, something of that sort. Okay. Okay. Bucket sorting. Again, you can think of, and we know we are going towards radix sorting with this, but you can think of bucket sort by itself as a way to break things into groups, right? Instead of saying, I'm going to take a sample, take a median, so to speak, and or k proxies, k pivots, and break the list into k sections based on those pivots. I can say, I don't care about pivots, I'm going to choose k random things, which gives me k buckets, p buckets, right? P is the number of processors, and then I'm going to do local sorting within the p buckets. If you now think in terms of, in the context of radix sort, then one way to make these buckets may be by range. Right? I assume that my list is uniformly populated by small integers, big integers, medium integers, all kinds of integers. And then I say, if you lie between 0 to and 1000, you go to bucket number 0, 1000 to something else, you go to bucket number 1, and so on and so forth. And you can see this is leading to taking fixed number of bits now per bucket, right? Because you can take all the common, you're basically making every number within a bucket have the same prefix. Of course, in a binary representation, you wouldn't say 0 to 1000, you would say 0 to 256 or 512 or things of that sort. And if it turns out that the numbers are really well distributed, then you can just stop here and do local sorting. If that local sorting is radix sorting, even better. And in fact, if we are assuming that this is an integer and we're dividing it based on integer or some hash of the key, which is an integer, which we are using to separate them, then radix sorting inside the local groups would make a lot of sense. Okay. So we've talked about parallel bucket sorting. So I won't repeat it here. We've talked about this already. If you want to choose samples, either now in the context of using the bit string representation of your key, or median style, less than equal, comparative style key. How do you choose these splitters is going to be one important question.
Sir, in radix sort, we can only divide in bucket if you are going from MSB to
So far what we have done is we have divided it into buckets and then done local sorting on each one of them, whatever the method for local sorting that you like maybe.
But in radix sort, if you are going from LSB to MSB, then we can't divide it in buckets.
No. This hasn't anything to do directly with radix sorting. Right? You're dividing it into buckets. You're sorting it into buckets, and then you may do radix sorting inside each of those buckets. So the first step wasn't really one step of radix sorting. It was just dividing it into things that are known to be in order with respect to each other.
And maybe a MSB radix something of that.
Inside each,
So the first one that divides.
you could think of it that way, but it's not really about radix sorting. Right?
Yeah,
It's about using the key or using some splitter. Either it's some bits of the key or the value of the key to decide which bucket it goes in. And the buckets are ordered. Right? So one bucket has only elements less than the next bucket, and so on and so forth. That's all.
But is there a requirement that the buckets are like more evenly filled?
There would be. Right? As soon as you start to say I'll have something like P buckets, you would want it to be approximately equally filled. Okay. When we start to have fewer than P buckets, then it's okay, because then more than one processor can be assigned to a bucket.
How do we do the bucket?
One way to do this is the thing called sample sort at the bottom. Right? It's just so it is a new name for bucket sorting, so to speak. It's also called sample sort, where we take some random number of samples. Okay, we have to determine what the good size would be. We'll sort the samples, and then we take every samples, take out one as a pivot. Okay, not going to again go through the analysis of this. This is a reasonably well used algorithm and has good probabilistic bounds as well, and you can get reasonably bounded probability. I don't recall the exact formula that it derives, which is a weird function of logs, but if you use log n sized sample set, and from that use B buckets, select B buckets from that, right? You're guaranteed to get probability which is practically constant of getting good balance. Okay. The other way to do the sampling is, if you want B buckets, choose B squared samples. Okay. I'm not going to go through the analysis all of this because there is much ground to cover in the limited time we have. We take B squared samples, sort them. Of those B squared samples, we pick every B element, which is going to be the pivot. Okay. Intuitively speaking, why should every Bth element form reasonably good pivots?
Then we are looking from each one of them and again performing. Probably the partition which we are getting after distributing these will be most likely to be equal.
But again, in somewhat quantitatively,
Uniform distribution.
if you assume uniform distribution, then everything works. This is all in the presence of, none of this analysis starts with the assumption of uniform distribution. Okay, because it's just the probability of a good pivot.
1 by the elements of sample are left of pivot 1.
Something of that sort, right? Because we have said that we have taken B elements or some enough number of elements and then sorted and picked every so often, which means we definitely know that there are enough elements we are not picking as pivots between the two pivots, right? Yeah, so in this case, that's what you were doing in log n size sample set also. In this case, we have exactly B. And the probability that those B are uniformly distributed, again without any assumption on the input, is going to be rather high. So maybe what I'm going to do is leave this analysis for you. This will be on the website, and you're welcome to ask me questions on this. That is in the wrong place. Let's get to the radix sort variant. The standard radix sorting works this way, right? We basically separate it out into parts and then find out where bucket sort basically in sequence of the parts of the key. So in order to bucket sort, what do you have to do? Again, it basically amounts to finding the rank of a key. And this is something that you can go back and kind of plug into also the quicksort version, where we are essentially separating it into two chunks or three if we have equal number of equal keys allowed. So how would you do radix sorting? Forget about what the slide says, which, as you may guess, I'm going to leave for you to read also. But just at a high level, what would the radix sorting algorithm do in parallel? I can't let somebody go on to the next key, right? It has to be done in sequence. So everybody should be focusing on this part of the key, or this key, sub-key, if you will. Maybe this is complicated enough that I should go through it too. Don't look at the slide, think about it.
In one processor, you take one partition and locally find the rank of each. How many, for example, if I'm starting with B, so how many A's are before me? And so then in one step, I have to sum all the A's to find how many, in the global array, how many A's are there, and I know my local rank of B, so I can find.
How do you get the local rank of B? Only among B, because everybody has to do prefix sum, right? Again, stepping back one step out. What are we trying to do? There are some different keys key values in this subpart, right? So let's take an example. We're sorting integers, okay, and we have one digit as one part. Okay, this digit can have ranges 0 to 9, and I would like all the zeros to go up, then 1s, then 2s, then 3s, then 9s. Okay. Now, how should it happen? Something like prefix sum would do it, right? But how?
Processor, when you have a 10-bit array for all the processor looks at the element.
N-bit array? 10-bit array, okay.
Writes a 1 wherever, whatever is the first bit, writes a 1 in that column. And go prefix sum on these columns.
So, it's a 10-bit array, array of 10-bit numbers. Is that what you
I
said?
just wanted to keep a 0, 1 if my first digit is 0, if my digit is 0 or 1.
So I'm at a given column of digits, and I want to figure out how many zeros there are, and at the same time figure out how many ones there are. In the worst case, I can do it 9 times, 10 times. I can first say how many zeros are there, then I'll say how many ones are there, then I'll say how many 2s are there. And this can be done standard prefix sum, right? In fact, I not only know how many zeros are there, I know which 0 am I. Can I do it all together? That's the question.
I was just seeing this.
Okay. Where I don't take 10 prefix sums, or if the key takes alphabet size is k, then k prefix sums. Okay. I think we have to stop here.